Let us continue our discussion on these low rank approximations. Okay, so this is something that we have been discussing in the last class as well, and we have seen that if you have singular value decomposition, then using singular value decomposition you can actually compute the nearest low rank approximation. But the thing is that in many cases, computation of singular values is not a very easy task. Okay, so it might be computationally really very difficult. And there exists another way in which one can obtain low rank approximations of given matrix. Okay, so suppose let A be a matrix that is a given matrix which is of the size R n by m. Okay, so this is the matrix that we have. And this matrix I will have X, which is n by R, and this matrix Y, this is the matrix X that I have, and this is the matrix Y that I have. Okay, so it will be of the size R by M. Okay, so these are the two matrices that I have. The entries in these matrices are unknown. I don't know the entries of these matrices. Okay, so this is the setting. A is a matrix which is of the size n by m. And what I really want to do, I want to compute nearest rank R approximation to A. Okay, so A is a given matrix and we want to compute the nearest rank R approximation to A. Using SVD, what will you do? Using SVD, you first write down A singular value decomposition sigma 1 u1 v1 transpose plus sigma 2 u2 v2 transpose plus so on and so forth, sigma n by m, let us say sigma m um vm transpose. Okay, so this is what you write down. Suppose m is the rank, m is the rank of A. Okay, m is the rank of A. Suppose this is the case, you can write this thing down as A, and now you compute A tilde, which is just sigma 1 u1 v1 transpose plus so on and so forth, sigma r ur vr transpose, and this A tilde you can think as a rank R approximation to A. Using singular value decomposition you can do this. You kind of forget the remaining singular values, but in order to be able to do this, what do you really want? What do you really want is that you should be able to compute this singular value sigma 1 up to sigma r u1 v1 singular vectors, left and right singular vectors, and computationally it may not be an easy task to do. Okay, computationally it may not be an easy task to do. So computationally, how one computes singular values, really computation of singular values is essentially done through something which is called as computation of eigenvalues of a matrix which is either A transpose A or AA transpose, right? So you compute these matrices AA transpose A and AA transpose. So this matrix we have already seen, we call this a Gram matrix. Similarly, this matrix AA transpose you have. And if you have A to be equal to U sigma V transpose, then what will be A transpose A? A transpose A will be V sigma transpose U sigma V transpose, right? Which will be equal to U sigma transpose sigma V transpose, right? So these sigma transpose sigma will have the eigenvalues of this symmetric matrix A transpose A, and V will have eigenvectors of this matrix A transpose A, orthogonal eigenvectors, right? So the square of singular values is what you will obtain as eigenvalues of A transpose A, and V basically the eigenvectors. And similarly, you can do the computation for AA transpose and then you can obtain U. So if you want to calculate singular values and singular vectors, which we all need, like all the singular values and all the singular vectors we need, you actually need to compute the eigenvalues and eigenvectors of A transpose A and AA transpose. So obviously computationally it's not a very good thing, because we have seen that once you increase the order of the matrix, the size of the matrix goes beyond degree 5. The polynomial characteristic polynomial, you cannot find out the exact roots because there does not exist a formula to compute the roots, like the formula that you all know for quadratic. right? So there is no formula, and computationally this is really a very big task, difficult task. Okay, so there are lots of algorithms. One of the important algorithms is Golub-Range algorithm, which actually calculates the singular values. So it is named after famous mathematician, actually pioneer in the field of matrix computations, by the Professor Golub. Okay, so he has written a very beautiful book called Matrix Computations, almost considered like the book in the area of computational linear algebra or matrix computations. Okay, so he had devised an algorithm which computed the singular values efficiently, but still computationally it is too much. Okay, so what I am going to really do here is that there is another approach and very interesting optimization technique involved in solving this particular problem. Okay, so what I start with is this matrix A, which is the matrix of the size R n cross M. And what I think is that I factor this matrix A as this matrix X times Y. Okay, I factor this matrix as matrix X times Y. So this is N cross R and this is R cross M. Y is of the size R cross M. And if both A and X and Y, the product is such that the product XY. So this product XY, I will roughly write down as XY, and this product XY will have rank R. Okay, it will have rank R. So this is what I'll have. And if this matrix is such, so if I'm able to find out matrices X and Y such that A can be approximately written as XY and the product XY has rank R. So I'll calculate all such matrices product XY, right? And what will I say? I'll say that I want to minimize this over the matrices X and Y of appropriate sizes. What are the sizes? Sizes of X is N cross R, R cross M. And whichever matrix X and Y together give me minimum of this particular cost function, I will choose that pair X and Y, and this problem can be solved computationally comparatively easily. Okay, so this problem is what I will really like to look at, and this problem, if I'm able to solve and if I can find out X and Y which minimize this cost function, then what I will really say is that I have found out the low rank approximation. And what is the low rank approximation? Rank R low rank approximation. The low rank approximation is actually this product XY, right? So that is what you have. Okay, so this is what I am really going to do. So this is a very famous formulation, and the reason why such a formulation actually is really very helpful is that we will see why this type of formulation is really very helpful. But once you understand this formulation, then we can go further. So is this formulation okay? Do you understand how I am getting this formulation? Is this part okay with you? Okay, and once you understand this part, so this is the formulation, okay, formulation for low rank approximation. And once you understand this part, then the next part is how do you solve this optimization problem, right? How do you solve this optimization problem? So any thoughts on how will you solve this optimization problem? So we have solved various problems, optimization problems in this class so far. So how do you solve this optimization problem? In general, do you have any thoughts about how to tackle this? So the first thing I want to ask is it a linear or non-linear, quadratic? What is the optimization formulation? What is this optimization problem? Does it look like a least squares problem? What do you think? Is this optimization easy to solve? What do you say? What do you think? So what we are really going to do here, what we really are going to do here is that this problem, yes.
Sir, like this would be a quadratic optimization in nm variables.
Yeah, but those nm variable quadratic optimization, the problem is, okay, so how do you nm? So how do you
So,
get nm number of variables?
sir, like we would be like, okay, but like nm variables, as in there would be nm entries, so that the whole matrix
No,
has rank
so
R.
no, so which, okay, so this is a good point. So I want to look at this also very carefully. So what is this? What are the unknown variables in this optimization problem? What are the decision variables? They are the matrices X and Y. Do you agree?
Yes, sir.
So how many unknown entries in matrix X are there?
nr,
NR. And how many unknown entries in matrix Y are there?
rm,
Rm. So how many decision variables are there strictly speaking? Not NM. They are NR plus
r
Rm. Do
times
you
n
see
plus m. Yes.
R times M plus N? Correct. So that R times M plus N can be much smaller than the product Mn if rank R is small. Do you agree?
Yes, sir.
Yeah, so it is not an optimization problem with nm number of variables. Nm number of variables optimization problem might be even more difficult to tackle. Here you have lesser number of optimization variables or decision variables as they call. The number of decision variables is, okay, so let us write this down. Number of decision variables is R times M plus N, right? So which is nothing but Rm plus Rn, and Rm is corresponding to matrix Y and Rn is corresponding to matrix X. Okay, so that part is done. Now when you have such a thing, you already have product of these variables, no? So basically when you take product xy, you will look at this particular first row of X, multiply it with Y, and then whatever you get, so these decision variables are multiplying with each other, right? And then because of 2 norm there is a quadratic cost function, right? So it is not purely quadratic, there is a product of decision variables also taking in place. Do you see that, Kshitish?
Yes, sir.
Yeah, so it is kind of complicated. If the product of decision variables were not taking place, then we could have just said it's a quadratic problem, right? But now the problem here is that there is a product of decision variables also taking place. So what we are going to do here is we are going to simplify this. Okay, so we have this matrix A, which is given matrix, and what do we want to find out? Find x hat and y hat. Okay, x and y hat with appropriate sizes such that norm of a minus xy. So let me write this down. X hat and y hat are basically nothing but argument minimum over x and y of a minus xy to norm. That is what we really are going to do. So what I am going to do is the following. Matrix A here is the given matrix, right? And both x and y are unknowns. Suppose if I say that one of the matrices x and y were known to me. Suppose hypothetically assume that I know x. Okay, so I'll consider x to be equal to x naught. Suppose x is equal to x naught is given. Okay, suppose this is given to me. Then what does this problem actually boil down to? Then you want to find out y hat such that what will happen? Such that y hat is argument minimum over y now because x is also given to me. And I have this a x naught y minimization of this 2 now. And what is this problem? Is this problem familiar? Is this problem familiar with you?
Least
Have we
squares
looked at it? Exactly. This is a least squares problem. We have solved this problem so many number of times in the course so far. So this is a least squares problem, and this least squares problem can be solved very quickly, efficiently, and the solution y hat can be computed for this particular problem. But what is the key? The key is that this particular assumption was made, that you started with the assumption that x naught was given to you. So x is equal to x naught is given. So suppose x is equal to x naught is given, then this problem becomes really very easy problem to solve. In fact, it becomes a least squares problem. You have a closed form solution for this particular least squares problem. And then you get what? You get y. But now what you will do? Now you use this particular value, I will call it y0 hat. So this is the value that is given to you. And then you will solve this this least squares problem. Okay, what least squares problem you will solve? You will think now that x is unknown and you work with this y0 hat. Then you solve this problem. Then what will you get? Suppose you get what you call x1 hat. Correct? Now you use this x1 hat to compute y1 hat. Then you use that y1 hat to compute x2 hat and so on and so forth. So do you understand where I'm going? So what I'm really doing is I'm alternating between these two minimization problems, right? Which two minimization problems? Once the minimization problem is with respect to x, once the minimization problem is with respect to y, and I'll keep on alternating between these minimization problems. So this original minimization problem was the minimization problem in two decision variables, two matrix decision variables x and y. Together that problem was difficult to solve. So what did I do? I kind of think x is equal to x naught. One decision variable is initialized and I solve the problem with the second decision variable alone. Why am I doing that? I'm doing that because solving the problem with only one decision variable is really very easy for me. It's just a least squares problem. And then I will alternate between these decision variables. Once I'll consider x as my decision variable, once I'll consider y as my decision variable, and whatever optimal values I have obtained in the previous iterations, I'll keep them as the initial condition or the given condition in my algorithm, and I'll keep on alternating between these two minimization problems. I'll keep on alternating between these two minimization problems until I get convergence, right? So these xi values and these yi values will start converging to some fixed point. And once they start converging, what x and y values you obtain as the this thing, those will be the optimal values for this particular cost function. You can actually prove this. Okay, there is a theory which proves that you do these iterations and eventually where this xi hat and yi hat sequence converges, these points will be actually the optimal points for this particular formulation, and you will get solution to this particular optimization problem. Okay, so this is what I'm really going to do. So is this part clear what I'm going to do? How am I going to iterate between these things? Is this part clear?
Sir, is convergence always guaranteed?
Yes, in this particular problem it is.
Okay,
Every time in general, in such a scenario where you are using alternating minimization trick, every time it may not be possible, but here it is possible. Okay, here it is fine. Is this part okay? Do you understand what we have done? So if I do this, then what I'm really doing is I'm just solving least squares problem in every iteration, for which I have a closed form solution available with me, and I use that closed form solution to quickly converge, hopefully, to these optimal x hat and y hat, optimal x hat and y hat values. So here are these x hat and y hat values. So I converge to these x hat and y hat through the sequences of xi hat and yi hat. Okay, so that is what I'll do. I'll iterate between these. I'll alternate between these minimization problems, and I'll converge here. One of the most important reasons why I really want to work with such an optimization formulation rather than a very nice closed form solution in terms of SVD is that if I have certain constraints on these low rank approximations. So this is a matrix factorization problem basically, right? So this will give you a low rank approximation, all right, but this is a matrix factorization problem also, right? So here, if I have a constraint that the entries of matrix X and Y are both non-negative, okay, so I want a low rank approximation of rank R, but there is a constraint. What is the constraint? The constraint is that I want all the entries in that matrix to be non-negative. Then this is a non-negative factorization. I can very easily take this further with a constraint, right? So with subject to, so I can add a constraint here. So in the formulation, I'll add the constraint x is greater than or equal to 0, y is greater than or equal to 0. So this greater than or equal to 0 symbol is basically element wise. Okay, it is not positive definite. It is element wise. Let us say, for example, then if these both matrices have non-negative entries, then what I'm really doing is that I'm factoring the given matrix A into product of two non-negative matrices with the constraint that the product xy has rank R, right? So that is what I have done. So it is similar to something which is called as non-negative matrix factorization. So this type of things have applications in natural language processing and so on and so forth. So these type of factorizations really play a key role. And because we have such a formulation available with me, if you do not have any constraint, then you are actually finding out low rank approximation of rank R to the given matrix A, really. But if you have constraints, then you can have these constraints in place, and with these constraints actually you can try to solve the optimization problem. And this is something that is really very important, though I am not going into the great details of theoretical convergence proofs and so on and so forth. These type of things can be actually guaranteed. Okay, there is literature, there are good papers around which talk of how to implement this in a computationally efficient way, and what are the guarantees on convergence under certain conditions and so on and so forth. So if you do not have any constraints here, then this alternating minimization will always have guarantee of convergence. Okay, so that is something that is really very important. So is this part kind of clear to you, what we have done here?
So one question,
Yes.
why won't x1 hat be equal to x0?
No, sorry, what is it?
Why won't x1 hat be equal to x0?
No, x1 hat cannot be equal to x0, right? Because y0 value is now different, right? So you have a least squares problem going on, right? You do not have exact solution available. If you have exact solution available, then what you are saying probably is right, but you do not have exact solution available. That's the problem. This equation A is equal.
Why not
This
value?
equation, I'll
Why
tell
not
you, this equation is not exactly going to be satisfied. Na? There is an approximation here. A is equal to xy. It is not exactly equal. And even if it is exactly equal, there can be many solutions to this. You not necessarily should get the exact same solution with which you started. These are the 2 points why you will not have x0 coming back. Is it okay, Harshal?
Yes, I got it.
Yeah. Because these matrices X and Y are also not square matrices, right? So you cannot think of, cancelling this y0, I will cancel y0 from both sides kind of thing. You cannot really do in matrices unless you have square matrix which is invertible. Do you get the point?
Yes, sir.
Yeah. Okay. Anything else? Okay, so this is something that is really very important, and this type of factorization has many applications. Okay, so one application which I am trying to explain here, though I don't know how well I'll be able to explain, but let me try. Okay, so most of you are aware of this neural network architecture. Okay, so consider this neural network architecture. So this neural network architecture is here, and here are certain nodes, and I have only one layer. Okay, I am only talking of one layer, and in this layer I have fully connected architecture. Okay, so I have fully connected architecture. So I'll connect every node with every other node. So this is input layer, this is output layer, right? So suppose you have this output vector. So suppose the length of output vector is, suppose there are, what was the size of matrix I had taken? N cross M. So suppose there are N output nodes and M input nodes. Okay, so there are M number of output nodes and number of input nodes. So your output is a vector of size N, right? This is the output, which is vector of size N. Okay. And this is the input, which is a vector of size M, right? I'm not considering any activation at this point. I'm not even considering bias at this particular point. I'm just looking at input and output layer, right? And fully connected input and output layer. So that is what I'm looking at. So first of all, how many number of weights are here? How many number of weights are here? Can you tell how many number of weights are here? If it is a fully connected layer, input to output fully connected layer, how many number of weights are here? And what is the relationship between output vector and input vector?
It will be mn weights if we don't trigger the bias.
Yeah, so I'm saying that
Hello.
Hi, can you hear me? Can you hear me?
Yes, sir.
Yes, sir. Yes, sir.
Okay, so sorry, the power went off in the campus. So my internet connection and everything went off. So I had to wait until the power was restored. So power is restored now, and I think this thing is working. But